Right, so as the last topic for our course, we have 3.7, which is about multiple eigenvalues. And by multiple, we mean repeated. So this can get a little weird. First of all, we should start with some terminology. So let's A be an n by n matrix. And let's lambda be an eigenvalue of A. So first of all, the algebraic multiplicity of lambda is the exponent of x minus lambda in the characteristic polynomial of A. So this is the normal multiplicity of a root of a polynomial that you're used to. If we have like lambda minus 2 squared in the factorization of the characteristic polynomial, then the algebraic multiplicity would be 2. If we have lambda minus 2 to the 15th, then the algebraic multiplicity would be 15. Okay? The geometric multiplicity of lambda is the largest possible number of linearly independent eigenvectors of lambda. Okay. In all of our examples so far, the algebraic multiplicity and the geometric multiplicity have both been 1. So, of course, today's topic is about when they're not 1. The defect of lambda is the algebraic multiplicity minus the geometric multiplicity. And furthermore, if so it's worth saying that the defect of an eigenvalue is always greater than or equal to 0. If the defect is 0, we say the eigenvalue is complete. If the defect is larger than 0, then we say that the eigenvalue is defective. Okay? So when you have complete eigenvalues, when the defect is 0, things go pretty smoothly. Let's look at an example where that happens. So we're going to find the general solution of the vector ODE -2, 0, 0, -2 times z vector, equals z vector prime. So the first thing we have to do is find the eigenvalues. So let's call this A. For all of today, the matrix is going to be called A. I'm not going to... I'm going to get tired of writing the same entries over and over, so I'm just going to call it A. Okay. So we need to set the determinant of A minus lambda I2 equal to 0. In our case, that's going to be the determinant of -2 minus lambda, 0, 0, -2 minus lambda. You do this determinant, you get -2 minus lambda times -2 minus lambda minus 0 times 0. This is lambda plus 2 squared. The negatives cancel because you're multiplying -1 by -1. Okay, so we have a single eigenvalue, lambda equals -2, with an algebraic multiplicity of 2. All right. Now let's inspect the eigenvectors. So to find the eigenvectors, what we need is A times v vector equals -2 times v vector, where v vector is not the 0 vector. Now let's notice that this can be rephrased as A plus 2i2 times v vector equals the 0 vector. Okay, we'll need to rephrase it like this for talking about generalized eigenvalues later today. Okay. In any case, this is going to be 0, 0, 0, 0 times AB equals 0, 0. Okay, so you multiply through, you get 0a plus 0b equals 0, 0a plus 0b equals 0. And you're like, okay, yeah, we already knew that. Yes, however, what this illustrates is that there is no restriction on what a and b can be, other than that they must not be both 0. Okay? So what we get here is the eigenvector, which I'll call v, ab. Well, this is a times 0 plus 0 times b, which I'd like to point out is a times 1, 0 plus b times 0, 1. Okay? Since a and b have no relationship, according to the fact that we did the multiplication and found no relationship between them, they can be anything. So we just have all the linear combinations of 1, 0 and 0, 1. 1, 0 and 0, 1 are linearly independent, so the geometric multiplicity is 2. And that means that the defect is 2 minus 2, which is 0. Okay? So now things go smoothly. Okay? We can pick two eigenvectors that are linearly independent. Let's name v1 Let's make it 1, 0. And v2, let's make it 0, 1. Linearly independent eigenvectors. So now we can construct basis solutions. z1 equals 1, 0, e to the negative 2t. z2 equals 0, 1, e to the negative 2t. And then in that case, the general solution is just going to be c1 times 1, 0, e to the negative 2t plus c2 times 0, 1, e to the negative 2t. And that's all you have to do. Okay? Now the trouble is, not every repeated eigenvalue is complete. Some are defective. And when you have a defective eigenvalue, you're going to end up with fewer linearly independent eigenvectors than you need to construct the basis solutions. So what do you do then? Well, what you do is you have to construct what are called generalized eigenvectors. So, another definition. Same thing, A is an n by n matrix and lambda is an eigenvalue of A. Given a positive integer let's call it k, a rank k generalized eigenvector corresponding to the eigenvalue lambda is a vector v, which is not the zero vector, such that A minus lambda in times v vector equals zero vector. If we had that, then we'd just be talking about an eigenvector, right? So we're not talking about this, we're talking about raising this matrix to the k power and then multiplying it by v. Okay. But if you raise it to the k minus 1 and multiply it by v, you do not get the zero vector. This means that what we've been calling an eigenvector so far could be understood as a generalized eigenvector of rank 1. Okay, so let's see how this works to find us the general solution of a defective system. Let's suppose we're dealing with 9, 4, negative 4, 1. Okay. Once again, we need to find the eigenvalues. We're still doing the eigenvalue method. It's just now, it gets a little weird. So we have to set the determinant of a minus lambda I2 to 0. This would be the determinant of 9 minus lambda, 4, negative 4, 1 minus lambda. You do that determinant, you get lambda minus 9 times lambda minus 1, where I've cancelled the negatives from the two, minus negative 4 times 4. This turns into lambda squared minus 10 lambda plus 9 plus 16, which is lambda squared minus 10 lambda plus 25. Okay. That can be factored. That can be factored as lambda minus 5 squared. And then we get the single eigenvalue 5 with an algebraic multiplicity of 2. Okay. So now let's inspect the eigenvectors corresponding to lambda, which is 5. So the eigenvectors would be solutions of a minus 5i2 times v vector equals the 0 vector. Yeah. Actually, I'm going to call this v1 because we're going to need generalized eigenvectors, and I'm going to call them v2. So a minus 5i2 looks like 4, 4, negative 4, negative 4. Multiply this by ab and get 0, 0. So we have 4a plus 4b equals 0. Negative 4a minus 4b equals 0. This makes it pretty clear that a has to be negative b. Okay? So the eigenvectors, they all look like ab. But if a has to be negative b, then that would just be negative bb. So this would just be scalar multiples of negative 1, 1. So the geometric multiplicity now is only 1 because we only have one free variable here. That's another way of rephrasing geometric multiplicity. It's the number of free variables that you have when you compute the eigenvectors. So the geometric multiplicity is 1. And that means the defect is 2 minus 1, which is 1. So we have a defective eigenvalue. Now, what's the problem here? Well, the problem here is that we can construct one basis solution, z1 vector equals negative 1, 1 times e to the 5t. And that's good. But according to our solution theorem, because this is a 2 by 2 matrix, we will need two linearly independent basis solutions. Okay? As it is, because the geometric multiplicity is 1, the most linearly independent eigenvectors we could have is only 1. So, therefore, we have this basis solution, but if you try to construct another basis solution based on only the eigenvectors, it's not going to be linearly independent. Okay? So we have a little bit of a problem. And this is the problem with every defective eigenvalue. So here's what we have to do. We have to consider generalized eigenvectors of rank 2. Okay? So before we do that, we need to look at what a minus 5i2 squared actually is. Because if we're going to consider generalized eigenvectors of rank 2, then we need to have a minus lambda i2 squared times v equals the 0 vector. Well, it would help if we know what a minus lambda i2 squared actually is. So let's compute that first of all. So, a minus 5i2 is 4, 4, negative 4, negative 4. We want to square that, so to square it means to multiply it by itself. And then you do this matrix multiplication. So let's see. 16 minus 16 is 0. 16 minus 16 is 0. Negative 16 plus 16 is 0. And then negative 16 plus 16 is also 0. So the matrix that we're dealing with is 0, 0, 0, 0. So generalized eigenvectors of rank 2 those would be solutions to that thing equals the 0 vector, which in this case looks like 0, 0, 0, 0 times, let's call it CD, equals 0, 0. So what vectors would satisfy that equation? Literally any of them, right? There's only two requirements. First of all, v2 must not be the 0 vector. But more importantly, v2 must not be an eigenvector. So that means that it can't be the 0 vector. It also can't be a scalar multiple of negative 1, 1. So let's make the arbitrary choice. v2 vector is going to be 1, 0. That is not a scalar multiple of negative 1, 1, so it's not an eigenvector. It's a generalized eigenvector of rank 2. Okay? So now what you have to do is you have to come up with an eigenvector that is compatible with this choice of generalized eigenvector. By compatible, what I mean is v1 vector has to be a minus 5i2 times v2 vector, which in this case is going to be 4, 4, negative 4, negative 4, multiplied by 1, 0, which is going to be 4, negative 4. And that certainly is an eigenvector, right? It is a scalar multiple of negative 1, 1. But the important thing is that it is compatible with v2. Okay? This is what we call a chain of generalized eigenvectors. Okay? And that's what we need to construct the general solution. So the other basis solution, so the first basis solution is just v1 e to the lambda t, right? The second basis solution is a little bit weirder. It's v1 t plus v2 e to the lambda t. Okay? So in our case, that's going to be 4, negative 4 times t plus 1, 0 times e to the 5t. Okay, and now finally we have two basis solutions. So we can construct the general solution as all the linear combinations of these. So negative 4, 4, e to the 5t. Or you can take negative 1, 1 e to the 5t. It actually doesn't matter. Wait, no, sorry. I meant to write 4 negative 4 e to the 5t. Although, like I said, it doesn't matter. You can take any scalar multiple right here and it would be fine. What matters is you have to have the right scalar multiple here. So add it to this C2 times 4t plus 1 negative 4t e to the 5t. And then that is our general solution. Okay. So this is always how it works when you have a defective eigenvalue. You have to find the eigenvalues. You find that one of them is repeated. That gives it an algebraic multiplicity larger than 1. Then you look for the eigenvectors, and you see how many free variables there are in the expression for the eigenvectors. If there's only one free variable, then the geometric multiplicity is 1, in which case the defect is 2 minus 1, which is 1. So then you can construct one basis solution, but in order to construct the other basis solution, you have to consider generalized eigenvectors of rank 2. So you look for generalized eigenvectors of rank 2 by squaring the matrix A minus lambda I2. That seems to always come out to be 0, 0, 0, 0. I can't think of an example where it's not the zero matrix. You might be able to prove that it has to be the zero matrix every time, but I don't know it off the top of my head. In any case, you're looking for vectors v2 that satisfy the equation zero matrix times that vector equals the zero vector. Well, literally any vector would do that, so just make a choice. Your choice has to be not the zero vector, and your choice has to be not one of the eigenvectors. But other than that, anything is fine. You find a compatible eigenvector by multiplying A minus lambda I2 by your generalized eigenvector of rank 2. Then you construct the basis solutions as v1t plus v2 e to the lambda t. Okay? So all that work just to find one more basis solution. It seems like a little bit of a ripoff, but it is how you do it. In any case, now you know why I saved repeated eigenvalues for the end. It's because it's the most complicated. Okay, so let's do another example. I'm going to erase this terminology now, so if you need to see it, I would suggest pausing the video. Okay, this one is the system x prime equals negative 5x plus y, and y prime equals negative x minus 3y. Okay. So to find the general solution of this system, first of all, we're going to convert it to a matrix equation. We're going to write this as z vector prime equals negative 5, 1, negative 1, negative 3 times z vector. Now we need to find the eigenvalues of that matrix, which again I'm going to call A. 0 needs to be the determinant of A minus lambda I2, which in this case is going to be the determinant of negative 5 minus lambda 1, negative 1, negative 3 minus lambda. You multiply through, or do the determinant rather, and what you get here is lambda plus 5 times lambda plus 3 minus negative 1 times 1. This turns into lambda squared plus 8 lambda plus 15 plus 1, which is lambda squared plus 8 lambda plus 16, or in other words, lambda plus 4 squared. So we get the single eigenvalue, negative 4, with an algebraic multiplicity of 2. Okay. Now let's inspect the eigenvectors to see how many free variables we have. And of course, because you know that the situation is easy if the geometric multiplicity is also 2, you know it's going to end up being 1. Of course I'm going to do that because that is the hardest example that we could come up with. So we need A minus lambda I2 times V1 vector equals the 0 vector. In this case, that looks like negative 1, 1, negative 1, 1 multiplied by, let's call it AB, is equal to 0, 0. You multiply through, you get negative A plus B equals 0, and negative A plus B equals 0. Therefore, A equals B. So when you write down the eigenvectors, you have AB, but A equals B, so that means this is BB. So that means this is B times 1, 1. There is one free variable in that, so we have a geometric multiplicity of 1. Therefore, a defect of 2 minus 1, which is 1. So, geometric multiplicity is 1, so defect is 2 minus 1, which is 1. So from this alone, we can construct one basis solution. We can make the basis solution z1 vector equals 1, 1 times e to the negative 4t. And that's great. But to construct the other basis solution, we need generalized eigenvectors of rank 2. Okay. So what we are looking for are solutions of a plus 4i2 squared times v2 vector equals the 0 vector. Where again, v2 had better not be the 0 vector, and also it cannot be one of the eigenvectors. So, a plus 4i2 squared, first of all let's figure out what that matrix is. This is going to be negative 1, 1, negative 1, 1 multiplied by itself. This comes out to be 0, 0, 0, 0 again. So what we are looking for, therefore, are solutions of 0, 0, 0, 0 multiplied by, let's call it CD, equals 0, 0. Well, literally any C and D would satisfy that. So you just have to pick one that's not 0, 0, and it's also not a scalar multiple of 1, 1. So let's take V2 will be 1, 0 for no particular reason. All right, so now finally, there's one more thing we have to do. We have to find an eigenvector that's compatible with this choice of v2. So that would be an eigenvector, that would be negative 1, 1, negative 1, 1 multiplied by 1, 0. That gives us negative 1, negative 1. And so now finally we can construct the second basis solution. This is going to be v1t plus v2 e to the lambda t, which in our case is going to be negative 1 times t plus 1, 0 times e to the negative 4t. And then you just take all the linear combinations of the two basis solutions, and that is the general solution. So 1, 1 e to the negative 4t, and negative t plus 1, negative t e to the negative 4t. And that is our general solution. Okay. Let's do another example. This one is x prime equals 7x plus y. Y prime equals negative 4x plus 3y. Okay. So once again, convert this to a matrix equation. We get z vector prime equals 7, 1, negative 4, 3 multiplied by z vector. We need the eigenvalues. So you take 0 equals the determinant of the matrix minus lambda I2, which in this case is going to be the determinant of 7 minus lambda, 1, negative 4, 3 minus lambda. You do the determinant, you get here lambda minus 7 times lambda minus 3 minus negative 4 times 1. This comes out to be lambda squared minus 10 lambda plus 21 plus 5. So we get here lambda squared minus 10 lambda plus 25. This is lambda minus 5 squared. We get lambda equals 5 with an algebraic multiplicity of 2. Okay. Then from here we inspect the eigenvectors. So we are looking for solutions of A minus 5i2 times v1 vector equals the 0 vector. This will be 2, 1, negative 4, negative 2. Really? Yeah. Yeah. Let me just make sure I didn't mess this up anywhere. We have lambda minus 7 times lambda minus 3 minus negative 4 times 1. Lambda minus, okay, lambda equals 5, so minus 5. Yeah. Yeah, okay. Times v1 vector, which we'll call AB. This needs to be the 0 vector. So you multiply through, you get 2a plus b equals 0, and negative 4a minus 2b also equals 0. Take either one of these equations, and what you're looking at says b equals negative 2a. Therefore, the eigenvectors look like AB, where b is negative 2a. So these are all the scalar multiples of 1, negative 2. All the non-zero scalar multiples of 1, negative 2. Okay? So from this we can construct one basis solution. 1, negative 2 times e to the 5t. Okay. But now to construct the other basis solution, we're going to need to find generalized eigenvectors of rank 2. So, once again, we're going to look at a minus lambda I2 squared, which is 2, 1, negative 4, negative 2 multiplied by 2, 1, negative 4, negative 2. You multiply through, this becomes, let's see, 4 minus 4 is 0. 2 minus 2 is 0. 8 plus 8 is 0. And then negative 4 plus 4 is 0. So just as typically, we get that this matrix is the 0 matrix. So now we're looking for solutions of 0, 0, 0, 0 times v2 equals 0, 0, which are not the 0 vector and which are not eigenvectors. Okay, so make the arbitrary choice. v2 is going to be 1, 0. We find an eigenvector that is compatible by multiplying a minus 5i2 by v2 vector. So that would be 2, 1, negative 4, negative 2 multiplied by 1, 0, which comes out to be just 2, negative 4. So now, the second basis solution is going to be v1 vector times t plus v2 vector times e to the lambda t, which in our case is going to be 2, negative 4 times t plus 1, 0 e to the 5t. And so then the general solution is all the linear combinations of these two basis solutions. 1, negative 2 e to the 5t, and let's see, 2t plus 1, negative 4t, e to the 5t. And there we have it. Okay. Let's do one more example. Let's say x prime equals negative 8x minus y. Y prime equals 4x minus 4y. Okay. So once again, convert this to a matrix equation. Z vector prime equals negative 8, negative 1, 4, negative 4 times z vector. We're looking for the eigenvalues, so 0 needs to be the determinant of a minus lambda I2. This is going to be the determinant of negative 8 minus lambda, negative 1, 4, negative 4 minus lambda. You do the determinant, you get lambda plus 8, lambda plus 4 minus 4 times negative 1. This turns into lambda squared plus 12 lambda plus 32 plus 4. In other words, lambda squared plus 12 lambda plus 36. This is lambda plus 6 squared. And so lambda equals negative 6 with an algebraic multiplicity of 2. Right, so now let's inspect the eigenvectors. So these would be non-zero solutions of A minus negative 6i2 times v1 vector equals the 0 vector. In our case, that looks like negative 2, negative 1, 4, 2 times AB equals 0, 0. Multiply through, and you'll get negative 2a minus b equals 0, and 4a plus 2b also equals 0. Either one of these equations can tell you that b has to be negative 2a. So, the eigenvectors all look like AB, where b is negative 2a. In other words, scalar multiples of 1, negative 2. So again, the geometric multiplicity is 1, which means the defect is 1. So we can construct one basis solution, 1, negative 2, e to the negative 6t. But then to construct the other basis solution, we're going to need generalized eigenvectors of rank 2. So let's look at a plus 6i2 squared. That's going to be negative 2, negative 1, 4, 2, multiplied by negative 2, negative 1, 4, 2, this equals, let's see here, 4 minus 4 is 0. 2 minus 2 is 0. Negative 8 plus 8 is 0. Negative 4 plus 4 is 0. So as usual, it turns into the 0 matrix. So we are looking for V2 that satisfy 0, 0, 0, 0 times V2 equals 0, 0. Literally any vector would do that. You just have to pick one that's not an eigenvector, and it's also not the 0 vector. So let's pick 1, 0 for no particular reason. Okay. And then from there, we're going to need to find a compatible eigenvector. So V1 vector needs to be A plus 6i2 times V2 vector, which in this case is going to be negative 2, negative 1, 4, 2, multiplied by 1, 0. And that just gives us negative 2, 4. Therefore, the second basis solution is going to be V1t plus V2 times e to the lambda t. That will be negative 2, 4 times t plus 1, 0 e to the negative 6t. And so our general solution is all the linear combinations of the basis solutions. 1, negative 2 e to the negative 6t plus negative 2t plus 1, 4 e to the negative 6t. And that is that. Okay. So when you see the defect is 1, it might ruin your day, depending on how large your matrix is. But ultimately, it's just a little bit more work to find the basis solution corresponding to the generalized eigenvectors of rank 2. In any case, that's all for today.